Hello everyone and welcome to this GitOps with ArgoCD series. In this course, we will learn the fundamentals of GitOps, understand why GitOps has become so popular in modern cloud native environments. Also, we will explore its relationship with Kubernetes and see how ArgoCD helps us implement GitOps in a practical way. By the end of this series, you will understand not only how GitOps works, but also how organizations use ArgoCD to automate deployments, improve reliability, and maintain consistency across Kubernetes environments. So let's start with the most fundamental question: what is GitOps? At its core, GitOps is an operational model where Git acts as the single source of truth. What does that mean? It means the desired state of our applications and infrastructure is stored in a Git repository. Whatever is defined in Git repository is considered the correct state, and our systems continuously work to ensure that the actual environment matches the desired state. The Git repository can be hosted anywhere, such as GitHub, GitLab, Bitbucket, Azure Repos, or any Git compatible repository. The key idea is simple. If a change is not in Git, it should not exist in the environment. In other words, Git becomes the central place where all configuration changes, deployments, and infrastructure updates are tracked, reviewed, and approved. Now, you might be wondering, why do we need GitOps in the first place? Well, traditionally, engineers often make changes directly in the environments. Someone logs into a Kubernetes cluster, updates resources manually, or modifies cloud infrastructure through a console. Over time, this creates inconsistencies because the actual environment no longer matches the documented configuration. So GitOps solves this problem by ensuring that all changes are made through Git. So every change becomes version controlled, auditable, reviewable through pull request, easy to roll back, and consistent across environments. This creates a standardized and a predictable deployment process. Well, one important thing to understand is that GitOps is not limited to Kubernetes resources. We can also manage infrastructure using GitOps principles. For example, tools such as Terraform allow us to define infrastructure as code and store that code in Git repositories. Using GitOps together with infrastructure as code, all infrastructure changes should flow through Git. For example, IAM roles, VPCs, EKS clusters, security groups, networking components can all be managed through code stored in GitOps repositories. So if someone modifies infrastructure directly in AWS, instead of updating the code in Git, a configuration drift occurs. Well, what is configuration drift? The difference between the desired state and the actual state is known as configuration drift. Drift can be detected using tools such as Terraform Plan, Terraform Cloud Drift Detection, AWS Config, Kubernetes reconciliation tools such as ArgoCD, etc. This helps teams to maintain consistency between what is defined in Git and what actually exists in the environment. Now let's understand GitOps for Kubernetes deployments. The same concept applies to Kubernetes deployments as well. Instead of manually applying manifest and making changes directly in the cluster, we store Kubernetes manifest in Git. These may include deployments, services, config maps, ingress resources, secret management configurations, Helm charts, etc. Well, what happens? A DevOps engineer updates Kubernetes manifest files in Git repositories and submits a pull request. The changes are then reviewed by another team member, and once approved, the pull request is merged into the target branch, such as the main branch or release branch. At this point, ArgoCD comes into the picture. ArgoCD continuously monitors the Git repository and compares the desired state stored in Git with the actual state running inside the Kubernetes cluster. When ArgoCD detects a difference, it automatically synchronizes the cluster to match what is defined in Git. This means the deployment happens directly from Git. As a result, changes are fully auditable, rollbacks become easier, human errors are reduced, the deployment process becomes standardized. So, GitOps is the practice of using Git as the single source of truth for application deployments and infrastructure management both, with automated systems continuously ensuring that the actual environment matches what is defined in Git. And when it comes to Kubernetes, one of the most popular GitOps tools used to achieve this is ArgoCD. Now that we understand what GitOps is, let's quickly look at the 4 fundamental principles of GitOps. These principles form the foundation of every GitOps implementation, whether you are using ArgoCD, Flux, or any other GitOps tool. The first fundamental principle of GitOps is that the system must be declarative. This means the desired state of the system should be described using declarative configuration files. In Kubernetes, the YAML manifests that we use are a perfect example of declarative configuration. For example, deployment, services, ingress, persistent volumes, config maps, secrets, etc. All of these are defined using YAML files. In these files, we describe the desired state of the application rather than the steps required to achieve that state. For example, we can specify how many replicas should run, which container image should be deployed, which port should be exposed, etc. In a GitOps model, these declarative manifests are stored in Git, and whatever is defined in Git becomes the desired state for the Kubernetes cluster. The second fundamental principle of GitOps is that the desired state must be versioned and immutable. This means all configuration changes are stored in a version control system such as Git. Whenever we make a change and commit it, Git creates a new version of the repository state. One of the most powerful features of Git is that it maintains a complete history of changes. The third fundamental principle of GitOps is that changes must be pulled automatically from Git. The official definition is software agents automatically pull the desired state declaration directly from the source. Let's understand this with an example. Suppose a developer updates a Kubernetes deployment manifest and commits the changes to a Git repository. Once the changes are reviewed and merged, a GitOps controller such as ArgoCD detects the update. ArgoCD continuously monitors the configured Git repository, and when it notices a change, it retrieves the updated manifest and synchronizes those changes with the Kubernetes cluster. This is often referred to as the pull-based model because the GitOps controller pulls the desired state from Git and applies it to the cluster. So this way, deployments are driven automatically by the changes stored in Git. This makes the deployment process more consistent, reliable, and auditable. Now, the fourth fundamental principle of GitOps is continuous reconciliation. This is one of the most powerful aspects of GitOps. GitOps controllers such as ArgoCD continuously compare the desired state stored in Git and the actual state running inside the Kubernetes cluster. If both states match, everything is healthy. However, if a difference is detected, the GitOps controller identifies the cluster of being out of sync and attempts to bring it back to the desired state. For example, imagine someone manually changes a deployment directly inside the Kubernetes cluster using kubectl. Now, the actual state of the cluster no longer matches the desired state stored in Git. Since Git is the single source of truth, ArgoCD treats the Git version as the correct version. Depending on the synchronization settings, ArgoCD can automatically revert the manual change and restore the configuration defined in Git. So this is also one of the security advantages of GitOps. Instead of multiple administrators making direct changes in the cluster, all changes are expected to flow through Git, where they can be reviewed, approved, and tracked. Now let's see CI/CD pipeline flow using Jenkins and GitOps. Well, by following GitOps principles, we can design a modern CI/CD pipeline that clearly separates continuous integration from continuous delivery. Well, traditionally, many organizations used Jenkins for both CI and CD. However, in modern Kubernetes-based platform, Jenkins is typically used for the CI part, while ArgoCD is used for the CD part by implementing GitOps practices. We commonly use Jenkins multi-branch pipelines to automate the CI process. Let's understand the flow. For the application source code, we have an application repository. The developer commits code changes to the application Git repository. For example, in the Cognexa project, let's assume we have a Spring Boot microservice application and its repository is called Cognexa app repo. This repository contains the application source code and supporting files such as pom.xml, Docker file, Jenkins file, etc. Whenever a developer commits code and raises a pull request, the Jenkins multi-branch pipeline is automatically triggered. The pipeline then executes multiple stages such as build code, run unit tests, SonarQube code analysis, build Docker image, and push Docker image to a container registry. The container registry could be Amazon ECR, Docker Hub, JFrog Artifactory, etc. At the end of the CI process, a versioned container image is created and stored in the container registry. For example, Jenkins may build and push the Cognexa-app and the image tag is 1.0.25. So this completes the continuous integration part of the pipeline. So this is part of CI, and at this stage, Jenkins has not deployed anything to Kubernetes yet. So for deployment, we use ArgoCD as the GitOps tool. So in the modern GitOps architecture, Jenkins is responsible for continuous integration, while ArgoCD is responsible for continuous delivery or deployment. Well, instead of Jenkins directly executing commands like kubectl apply-f deployment.yaml or any manifest.yaml, all deployment configurations are stored in a separate GitOps repository. For example, for the Cognexa project, let's say Kubernetes deployment repository is called Cognexa config git repo. This repository contains the desired state of the application deployment and it can be implemented using plain Kubernetes manifest, Helm charts or Kustomize. So once a new application image is built and pushed to the Docker registry, the deployment configuration needs to be updated to reference the new version. Well, there are multiple ways to achieve this. One common approach is that a separate Jenkins pipeline automatically updates the image tag in the GitOps repository. For example, after building Cognexa app version 1.0.25 image created, the pipeline updates the deployment manifest or Helm values file in the GitOps repository with the new image tag and commits the changes back to Git. Another common approach is that the DevOps team or platform team manually updates the deployment configurations through pull requests. And these changes may include image tag updates, replica count changes, resource requests and limits, environment variables, ingress configuration, Helm values, or any other deployment related configuration. Just like application code, all configuration changes are reviewed and approved through Git before they are deployed. Now this is where ArgoCD comes into the picture. ArgoCD continuously monitors the GitOps repository and compares the desired state stored in the Git with the actual state running in the Kubernetes cluster. And whenever a change is detected in the configured branch, ArgoCD automatically synchronizes the Kubernetes cluster to match the desired state stored in Git. Since ArgoCD follows a pull-based mechanism, it pulls the latest deployment configuration from Git and applies it to the target Kubernetes environments. Well, this approach ensures Git remains the single source of truth, no direct kubectl access is required, full auditability through Git history, and automatic drift detection. After successful testing in SIT environment, the application is ready to be promoted in the next stage, which is UAT. To promote the application, the UAT deployment configuration in the GitOps repository is updated. This may involve updating the image tag or making other environment specific configuration changes required for UAT. Once these changes are committed and approved in Git, ArgoCD detects the updates in the UAT configuration and synchronizes the UAT Kubernetes cluster with the desired state stored in the Git. Well, remember, Git remains the single source of truth again, and ArgoCD continuously ensures that the actual state of the UAT cluster matches what is defined in the Git repository. As a result, the application gets deployed into the UAT environment. After UAT validation and business sign-off, the application is ready for production deployment. In many enterprise organizations, production deployments require approval through a Change Advisory Board (CAB) process. Once the CAB approval is obtained, the production-related deployment configuration is updated in the GitOps repository. This could include image tag updates, configuration updates, environment-specific settings, resource configuration changes, etc. After the changes are merged into production configuration, ArgoCD detects the updates and synchronizes the production Kubernetes cluster accordingly. This triggers the deployment in the production environment. Well, this way, the exact same image that was tested in SIT and validated in UAT is eventually promoted to production. One important point I would like to highlight here is that ArgoCD can manage Kubernetes deployments using several approaches for storing and managing configurations in Git repositories. Let's quickly look at the most common approaches used in real-world projects. The first one is plain Kubernetes manifest. This is the simplest approach to store plain Kubernetes YAML manifest in Git. In this approach, all Kubernetes resources are defined directly to YAML files and ArgoCD deploys them to the cluster. This approach is simple to understand and works well for small or less complex applications. The second approach is to use Helm charts. Helm provides templating capabilities that allows us to reuse configurations and generate Kubernetes manifest dynamically based on input values. This makes application packaging, configuration management, and deployment much easier, especially when managing multiple environments. As a result, Helm is one of the most widely adopted deployment approaches in Kubernetes environments. The third approach is Kustomize. The base directory contains the common Kubernetes manifest that are shared across all environments. For example, deployment, service, config map, and other common resources. The overlays directory contains environment-specific customization. For example, for dev, SIT, UAT, production, etc. Each overlay can override specific configurations such as replica count, image tags, resource limits, environment variables, ingress settings, etc. This allows us to maintain a single common base configuration while customizing only the environment-specific settings. Kustomize is very popular in enterprise environment because it helps reduce duplications and keeps configurations easier to maintain. Well, all three approaches, plain Kubernetes manifest, Helm charts, and Kustomize, are fully supported by ArgoCD and are widely used across enterprise Kubernetes platforms. So that's all for today's session. In the next video, we will dive deeper into ArgoCD architecture and components and understand how ArgoCD works internally to implement GitOps in Kubernetes. If you found this video helpful, please don't forget to like, share, and subscribe. Thanks for watching and happy learning.